Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is power measurement in balanced three-phase AC systems. Our objective is to examine different methods of power measurement for balanced three-phase AC systems. We'll examine the 3 wattmeter method and the single wattmeter method and discuss the advantages and disadvantages of these techniques. This lecture operates under the presumption the viewer has more than a passing familiarity with the analysis of balanced and unbalanced 4-wire Y, 3-wire Y, and delta configurations in three-phase AC systems, as illustrated in the three-phase AC examples lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. So don't bog this lecture down in lengthy calculations. Let's just use the results of the aforementioned three-phase AC examples lecture as a jumping-off point for our discussion. If you recall, we calculated the electrical properties of a balanced configuration of 3 load elements, where each element is modeled as an impedance of 425 ohms at an angle of 40 degrees when configured as a balanced 4-wire Y, a balanced 3-wire Y, and a balanced delta configuration in a 60 Hz, 120, 208 volt three-phase AC system. Then we modified one of the impedances to 345 ohms at an angle of 30 degrees and analyzed an unbalanced 4-wire Y, an unbalanced 3-wire Y, and an unbalanced delta configuration in the same 60 Hz, 120, 208 volt three-phase AC system. Let's restrict ourselves to the measurement of power in balanced three-phase AC systems for this particular lecture. We'll examine power measurement in unbalanced three-phase AC systems in a later lecture detailing the 2 wattmeter method. The results for the balanced configurations appear before you. You may want to take a screenshot of this data, particularly the line-to-line voltages, the line current, and total power figures, because we'll be referencing this set for several illustrated examples. You should note some very predictable outcomes that highlight how these different balanced configurations interact with the three-phase AC systems. Let's zoom in on each data set. Here's the data for the balanced 4-wire Y configuration. Note each branch impedance directly experiences a smaller line-to-neutral voltage, where each line-to-neutral voltage has a relative 120-degree shift between the other phases. Load current magnitude through each identical load impedance exhibits the same magnitude and the same relative phase shift. As a result, each load impedance experiences the same amount of apparent, real, and reactive power. Total apparent, total real, and total reactive power would be an individual apparent, real, and reactive power figure times 3. In the balanced condition, there exists no current in the neutral line. Given the balanced condition, no current exists in the neutral line, and we can effectively remove it from consideration. This is unsurprisingly called a balanced 3-wire Y configuration, and we can retroactively apply the previously calculated balanced 4-wire properties to this 3-wire Y arrangement. You'll again note each individual load impedance in a balanced 3-wire Y configuration experiences the same voltage magnitude, the same current magnitude, and the same relative phase shift. As a result, each load impedance experiences the same amount of apparent, real, and reactive power. Total apparent, total real, and total reactive power would be an individual apparent, real, and or reactive power figure times 3. You'll note for Y configurations, it's often a recommended practice to reference everything with respect to one of the line-to-neutral voltages, in this case L1 at 120 volts at an angle of 0 degrees. If you wanted to be hard-headed about this and reference all your calculations with respect to one of the line-to-line voltages, you'd have to shift these results 30 degrees clockwise or negative 30 degrees. Finally, here's the data for the balanced delta configuration. Note each load impedance in the balanced delta directly experiences the larger line-to-line voltage differential, where each line-to-line voltage differential has a relative 120-degree phase shift between the other phases. Load current magnitude through each identical load impedance exhibits the same magnitude and the same relative phase shift. As a result, each load impedance experiences the same amount of apparent, real, and reactive power. Total apparent, total real, and total reactive power would be an individual apparent, real, and reactive power figure times 3. In the balanced condition, line current magnitude is square root 3, or approximately 1.73 times load current magnitude, and exhibits a relative 30-degree offset from the nearest load current. You note for delta configurations, it's a recommended practice to reference everything with respect to one of the line-to-line voltages, in this case L1, L2 at 208 volts at an angle of 0 degrees. If you wanted to be hard-headed about this and reference all your calculations with respect to one of the line-to-neutral voltages, you'd have to shift these results by positive 30 degrees or 30 degrees counterclockwise. Comparing the balanced Y and balanced delta configurations, you'll note that the load impedances of the delta configuration experience a voltage magnitude square root 3, or roughly 1.73 times larger than that experienced by the same loads in the Y configurations. As a result, they draw a current square root 3, or roughly 1.73 times larger than that experienced by the same loads in the Y configuration, Given power is a product of voltage and current, the loads in the delta configuration experience square root 3 times square root 3, or roughly 3 times the power. The larger point for this particular lecture, focusing on three-phase AC power measurement, being this. You already know how to calculate and measure power in three-phase AC systems. AC power consists of real and reactive components, and these different dimensions of power can be calculated for an individual element using any one of the numerous methods at our disposal. Power for an individual load is the complex conjugate of load voltage times load current. Additionally, power for an individual load is the complex conjugate of load voltage squared divided by impedance. And finally, power for an individual load is the complex conjugate of load current squared times impedance. Total apparent, total real, and total reactive power for any three-phase AC system is simply the summation of individual apparent, real, and reactive power figures, and will remain so whether the load is balanced or unbalanced, Y or delta, black, brown, red, orange, yellow, green, blue, purple, gray, or white. Again, calculating power for individual elements should be well within your capacity. Total power is simply the summation of individual powers. If one wanted to experimentally measure power for any system, one could put 3 voltmeters and 3 ammeters inside a circuit and simply summate the results for the 3 individual loads. Through sheer brute force and stubbornness, this would yield the correct results every single time. A slightly easier technique is through the use of a device known as a wattmeter, where a wattmeter is a device that simultaneously measures voltage across and current through. In this case, the voltmeter portion of the wattmeter, the plus and minus connections, directly measures voltage across a load, and the ammeter portion of the wattmeter, the in and out connections, directly measures current through an individual load. Old school analog wattmeters featured a needle scale and often restricted themselves to the practical measurement of real power in units of watts only. However, more modern power measurement devices can offer different modes, similar to the DC and AC modes for a DMM, that allow a user to toggle between the apparent, real, and reactive portions of power. Let's assume we've got a super fancy power measurement device that allows this ability. Again, a wattmeter is a device that simultaneously measures voltage across and current through. 3 wattmeters hooked in the following fashions could measure power experienced by the 3 individual loads inside our various configurations. If we summated the figures displayed by this army of wattmeters, they would yield our total apparent, our total real, and total reactive power experienced by these systems. This is unsurprisingly called the 3 wattmeter method, and it will yield correct results every single time, whether the load is a 4-wire Y, a 3-wire Y, or a delta configuration, and whether the load is balanced or unbalanced. The 3 wattmeter method is a reliable and robust technique that really lets a user know what's happened to each individual load at any point in time. This being said, implementing the 3 wattmeter method is, to use a term I ordinarily reserve in describing your lazy lab partner's academic career, a total goat show. Not only is it expensive and time-consuming to implement the 3 wattmeter method, it necessitates actively digging into the loads to access the test points. The exception being a 4-wire Y configuration in which all test points are externally accessible. Some loads, like motors, don't facilitate invasive inspection. Might there not be an easier way of measuring power for 3-phase AC systems? Humans have a reputation of being lazy cheapskates, and a large portion of our cognitive resources are devoted to recognizing and taking advantage of patterns. A glaringly obvious, supermassive shortcut for balanced load conditions exists that I'm certain you've recognized by now. Given each individual apparent, individual real, and individual reactive power figure for a balanced load condition is identical, one could simply measure these same properties for an individual element and just multiply it by 3. Let's examine one such method of doing so. For a balanced 4-wire Y configuration, a single wattmeter hooked in the following fashion could easily measure power experienced by load impedance Z1. Given the data from our previous illustrated example problem, the voltmeter portion of the wattmeter would measure 120 volts at an angle of 0 degrees from line L1 to the externally accessible neutral wire. The ammeter portion of the wattmeter would measure 282.4 milliamperes of current at an angle of negative 40 degrees through line 1 and load impedance Z1. A relative phase shift of 40 degrees exists between voltage and current. This corresponds to a lagging power factor of roughly 0.77. An application of any of the AC power formulas yields 33.9 volt amperes of apparent power, of which 26 watts is directed towards real power and 21.8 vars is directed towards a reactive interchange. Multiplying this single figure by 3 yields a total apparent power figure of 101.6 volt amperes, of which 77.9 watts is directed towards real power and 65.3 VARs is directed towards the reactive interchange. By the way, this method, despite the fact we're making use of a single wattmeter, is not the official single wattmeter method, which we'll examine in a moment. For a balanced 3-wire Y configuration, we could hook up our wattmeter in the following fashion. Note the voltmeter portion of the wattmeter, the positive and negative connections, measures 120 volts at an angle of 0 degrees from line 1, not to an externally accessible neutral line, but rather to the central node formed by the Y configuration of load impedances. The ammeter portion of the wattmeter, the in and out connections, still directly measures 282.4 milliamperes of current at an angle of negative 40 degrees through line L1. As with the balanced 4-wire Y configuration, if we multiplied the values displayed by this wattmeter by 3, it would yield a total apparent power figure of 101.6 volt amperes, of which 77.9 watts is directed towards real power and 65.3 VARs is directed towards a reactive interchange. For a balanced delta configuration, we have to get a little bit more invasive, because we'd have to hook up our wattmeter in the following fashion. The voltmeter portion of the wattmeter, the positive and negative connections, measures 208 volts at an angle of 0 degrees from line L1 at node A to line L2 at node B. The ammeter portion of the wattmeter is buried deep inside the delta configuration. In this case, the in and out connections directly measure 489.4 milliamperes of current at an angle of negative 40 degrees through load impedance ZAB. As with our previous balanced configurations, if we multiply the values displayed by this wattmeter by 3, it would yield a total apparent power figure of 305.4 volt amperes, of which 233.9 watts is directed towards real power and 196.3 VARs is directed towards the reactive interchange. As effective as this method is, it is not without its drawbacks. The obvious drawback being that this method is suitable only for the balanced load condition, in which every load impedance forming the Y or delta is identical and voltage magnitudes are the same and phase shifted by a relative 120 degrees. If any load inside the configuration of interest wasn't identical, including the one being directly measured, we'd be getting an erroneous picture of the larger system because we're really only looking at 1/3 of the picture. The not-so-obvious drawback to this method is its unwieldiness and impracticality in real-world analysis scenarios. The balanced 4-wire Y configuration is perhaps the only configuration that easily lends itself to this technique, principally because the wattmeter is external to the load. Notice the voltmeter portion of the wattmeter is measuring voltage from an externally accessible line to the externally accessible fourth neutral wire. Similarly, the ammeter portion of the wattmeter is measuring current through an externally accessible line. Not so in the balanced 3-wire Y configuration, principally because the voltmeter portion of the wattmeter is measuring voltage from an externally accessible line to the central node internal to the Y configuration of load impedances. The ammeter portion of the wattmeter is still external to the load, but the voltmeter portion needs to dig into the load to take a proper reading. What if this central node internal to the 3-wire Y configuration was inaccessible? Oftentimes it isn't, the classic example being a 3-phase AC Y-configured motor where 3 ends of the Y configuration of balanced windings are externally accessible, however the central node is locked up tight. Directly measuring current external to a balanced 3-wire Y configuration is not a problem. Directly measuring voltage is. Balanced delta configurations present a similar disadvantage, only with respect to current measurement. Note the voltmeter portion of the wattmeter is directly measuring voltage from an externally accessible line to another externally accessible line, A to B. The ammeter portion of the wattmeter is, however, measuring current through a load buried deep inside the delta configuration. Oftentimes, the delta configuration is fixed and inaccessible, the classic example again being a 3-phase AC delta configured motor, where the 3 points of the delta configuration of balanced windings are externally accessible, however the configuration cannot be broken to incorporate an ammeter in series. Directly measuring voltage external to a balanced delta is not a problem. Directly measuring current is. In summary, balanced 4-wire Y configurations are open books and allow a single wattmeter to directly measure voltage and current through any impedance. In contrast, balanced 3-wire Ys and balanced deltas often hide their inner workings, making direct measurement of voltage in the case of the 3-wire Y configuration or the direct measurement of load current in the case of a delta an impracticality. Might there not be an easier, cheaper way to measure these properties external to the balanced load, regardless of configuration? Indeed there is. This technique is known as the single wattmeter method, and it takes advantage of balanced load conditions to measure total power, regardless of configuration. In each occasion, the single wattmeter method measures the line-to-line voltage and line current external to the load and does not necessitate invasive inspection. At first, you might think this won't work because of some glaringly obvious oversights. In the case of the balanced Y configurations, the ammeter portion of the wattmeter appears to be reading current correctly, as line current equals load current in Y configurations. However, loads in balanced Y configurations don't directly experience the line-to-line voltage, but rather a smaller portion of it. Taken in isolation, this wattmeter's reading is extremely suspect since it's artificially inflating voltage. Essentially, the opposite problems hold true in the case of balanced delta configurations. In this application, the voltmeter portion of the wattmeter appears to be reading voltage correctly, as loads in delta configurations directly experience the line-to-line voltage. However, loads in balanced delta configurations don't directly experience the line current, but rather a smaller portion of line current. Taken in isolation, this wattmeter's reading is again extremely suspect since it's artificially inflating current. In summary, the single wattmeter method seems to be measuring the line-to-line voltage and the line current regardless of configuration, properties that may or may not be representative of actual conditions inside the given configuration. Neglecting phase shift and power factor considerations, the magnitude of apparent power delivered to any load is the load voltage times the load current. This is true for any load regardless of configuration. If the system is truly balanced, we can say total apparent power equals an individual apparent power figure times 3. This should be pretty self-evident. To understand how a single wattmeter can yield a total power figure for a balanced system, it's helpful to remind ourselves about those properties unique to balanced load conditions. For balanced Y configurations, you'll no doubt recall that line-to-line voltage is square root 3, or roughly 1.73 times as large as load voltage. Additionally, for balanced Y configurations, line current is equal to load current. Balanced delta configurations, in contrast, experience line current magnitude that is square root 3, or roughly 1.73 times as large as load current. Additionally, for balanced delta configurations, load voltage is equal to line voltage. Follow the chain of logic for the balanced Y configurations. The single wattmeter is measuring line-to-line voltage and line current. For balanced Y configurations, line-to-line voltage is square root 3 times load voltage. For balanced Y configurations, line current is equal to load current. Follow the same chain of logic for balanced delta configurations. The single wattmeter is again measuring line-to-line voltage and line current. For balanced delta configurations, line current is square root 3 times load current. For balanced delta configurations, line-to-line voltage is load voltage. Both occasions result in the single wattmeter method indirectly measuring square root 3 times load voltage times load current. Recall that total apparent power for a balanced three-phase AC system is 3 times load voltage times load current. All we need to yield a total power figure is to simply multiply the single wattmeter method's reading by square root 3. Can you dig it? Square root 3 times square root 3 is 3. Importantly, this method is valid for either balanced load configuration, Y or delta, and is external to the load and does not require invasive inspection.